Polymorphism refers to the ability of some substances to crystallize into multiple different crystal structures. It's a remarkable property and something that's very difficult to predict, the actual structures that a molecule can crystallize into, or a salt, for example. But what there's another problem, and that's once you know the different structures that are out there, the different polymorphs that could result, how do you know when nucleation occurs which polymorph will result from the nucleation process? So one of them is a matter of knowing the polymorphs that exist, and the other one is a matter of knowing the kinetics that determine the relative selectivity of those polymorphs. So we refer to this problem as polymorph selection, the one that has to do with the kinetics. And it's an important problem for things that range from biomineralization processes. For example, calcite, aragonite, and vaterite are all different polymorphs of calcium carbonate. You can see from these pictures they have very different physical properties. They are also made by different organisms and used in different parts of their bodies. So the urchin makes its teeth out of calcite. The abalone makes parts of its shell out of aragonite, and it's actually the part that gives the pearls their luster. Humans make pearls as well. They are gallstones, and they are largely made of vaterite. So you have many examples of polymorphism in pharmaceutical molecules and small organic molecules. This famous example from Leon Yu's group looks at the compound red, orange, yellow, ROY, as it's now known, because each of its polymorphs has a different color, different crystal habits, and these crystal properties are very important for understanding how to formulate drugs, for example, and process crystalline pharmaceuticals. You don't want these little needles. You want instead things that are compact shapes so that you can process things easily. A very famous example that really clarified just how important this problem is the case of the ritonavir HIV drug from Abbott Pharmaceuticals. They developed plants and were in production and got permission to sell Form A, and then it turned out later that they found 3 other forms of this drug, and they could no longer make Form A. The plant in Singapore started making Form B, and they had to shut down their operation and reformulate the drug. By the time it was all said and done, the new formulation of the drug that could reliably make the form that they had permission to sell was much more expensive. They ended up having to raise the price of the drug and then faced a class action lawsuit for doing that. So this really got the lawyers involved and clarified that understanding polymorphism is a very industrially important goal if you're going to crystallize anything on the pharmaceutical front. So what governs polymorph selection? And there are a few different ideas about this. This is the second installment of my little lectures on polymorph selection. What I want to do here is sort of go back and provide some background information. Many people will tell you that Ostwald's rule governs polymorph selection. And Ostwald's rule says that if you have 2 different polymorphs that can crystallize, the one that comes out of solution first is the one that is least stable. Okay, so this is a rule that definitely occurs many times, and it's a rather curious thing. Why does the kinetics favor the less stable thermodynamic product? There's no obvious reason why it should do that. But also there are many counterexamples. In fact, every time an experimentalist tells you that when I crystallize substance A with this additive, I get polymorph 1, and when I don't use the additive, I get polymorph 2. That little tiny trace additive, in many cases, is affecting a change in polymorph selection. And the fact that you can change polymorph selection with a little trace additive means we know that the additive is not changing the relative stability of the 2 different polymorphs. So it must be doing something different. And so that's sort of a definite case where we can look at Ostwald's rule and say that it must not be the entire story. Stranski and Tatamanov amended Ostwald's rule, and they said we shouldn't look at the bulk thermodynamics of the 2 structures that can result. We should instead look at the nucleation barriers, the free energy barriers along the path, leading you from the metastable state to either of these 2 polymorphs. So they envision that you have one path that leads you to state A and another path that leads you to state B, for example. And if you think of these as both roughly obeying trends of classical nucleation theory, then in classical nucleation theory, the only reason that we have a nucleation barrier is because there's an interfacial free energy. And so we would expect that the higher the interfacial free energy, the larger the barrier associated with the nucleation process. And so that this view of Stranski and Tatamanov, I think, is probably very closely related to differential values of interfacial free energy between two different polymorphs and the mother solution. The other lecture on polymorph selection discusses a possible third explanation for polymorph selection, and that is where you have dynamics controlling polymorph selection. So the idea there is just that one polymorph can naturally grow faster than the other because the atoms from the surrounding solution have an easier time attaching and detaching from that nucleus, and the one that has the faster attachment and detachment frequency is able to grow faster and will eventually dominate through a process that really looks a lot like growth, but also can appear, those dynamics also appear in the prefactor of the nucleation rate. So it's not just about barriers, it also should include a consideration of the prefactor, and sometimes those prefactors are quite important. So if you are interested in hearing more about the dynamical explanation, see the other polymorph selection video. And here, what I'm going to do is go through and outline how we can actually analyze things from the viewpoint of Stranski and Tatamanov, which is really coming down to looking at differences in interfacial free energy between different polymorphs. Okay, so if we look at glycine, this little guinea pig molecule for studying polymorph selection, it's the simplest amino acid. It's a Zwitter ion. We can crystallize glycine in water, and what we find, well, we do everything in a computer, but what we find if we look at the literature and look at crystallization experiments is that in water, the polymorph that comes out of solution is alpha glycine, and you can put various additives in and encourage the formation of gamma glycine instead. So these are the two most commonly seen polymorphs that come out of nucleation experiments for glycine. Now, what we've done here is, and this is work done by my student Nathan Duff. I don't have the reference here written on the slide, but Nathan Duff is now at NCSU doing a postdoc with Eric St. Tiso. So this is the gamma glycine polymorph. I have not shown any of the water molecules in solution around it. I'm also not showing the glycine that's out in solution as well. I'm only showing those glycine molecules that are part of a dense cluster. And if a glycine is in a part of the dense cluster, but it's not very structurally ordered, then it's colored gray to indicate that it's part of a surface melted layer. When it's colored red, that indicates that it's part of a glycine-like environment, a gamma glycine-like environment that's structured like the crystal gamma glycine structure. When it's colored blue, that's to indicate that it is in an environment that resembles the structure of alpha glycine. Okay, so what you can see is that alpha glycine doesn't have a very thick surface melted layer, and gamma glycine does have a very thick surface melted layer. In fact, this is something like 7 or 8 angstroms thick. When you add salt, the situation changes quite a bit. Adding the salt doesn't do much to the alpha glycine polymorph, but it really changes the surface structure of the gamma glycine polymorph. Note that the salt has sort of partitioned. We have the gamma glycine polymorph is polar, so one of the two faces of this crystal was positively charged and the other one was negatively charged. When you add the salt, you screen out those uncompensated charges, and that allows this surface melted layer to heal, and it becomes basically very thin, just like the alpha glycine surface. So the salt effectively allows the crystal structure of the gamma glycine to remain uninterrupted all the way up to the interface with the surrounding brine, whereas in water, as it approached that interface that was charged, it started to become disordered. Okay, so the brine is effectively acting to, one, passivate those unscreened charges that were on the surface before, and it's also helping heal all these massive amounts of structural defects that you have around the surface in this melted layer region. Now you can imagine that what the brine is effectively doing then is lowering the interfacial free energy gamma. Okay, now remember in the classical nucleation theory that the log of the rate is the log of a prefactor minus a barrier parameter divided by the log of the log squared of the supersaturation. Now The barrier parameter is proportional to the interfacial free energy cubed. So if we do something that lowers that interfacial free energy, we should have a huge effect because it gets cubed and because it's inside the exponential. It should have a huge effect on that nucleation rate through this barrier parameter. So you can roughly anticipate here many of the effects that we've seen by just looking at Debye-Huckel theory. We were assisted in this effort by Kevin Schmit over at Kansas State University and his graduate student Yahub Dahal. And the qualitative thing that we anticipate would happen is that if you add salt, you will lower that interfacial free energy, and that will have the effect of lowering the barrier, leading to faster nucleation of gamma-glycine in brine than when it was in water. This is just a schematic. Haven't actually computed this result as yet, but I'll say some quantitative things about this in the next slide. We don't expect that the salt will have much effect on the water, the alpha glycine crystal structure, because there are no charged interfaces to really interact with there. So can we do this analysis quantitatively? Well, we can, and we were actually motivated by a more general question, and that's, can we quantitatively predict the effect of an additive that might be designed to help crystallize one particular polymorph over another one? So you can imagine the situation where I have 2 cups of water. One cup is full of pure water, and the other cup is full of brine, okay? Or my solution with my additive. And now we imagine that we take the crystal, and we start the crystal in the solution with the pure water. And what we want to do is to reversibly transfer that crystal from the solution with the water into the solution with the additive, okay? The effect of doing that is that the bulk of the crystal didn't change, and these 2 solutions that it's been immersed in didn't change. What's changed is only the interaction at the surface of that crystal with the surrounding solution. Okay, so by doing this process reversibly, we would isolate the effect of the change in the effect of those additives on the interfacial free energy of that nucleus. And this we call this delta F transfer property. So we can't actually reversibly move a whole crystal in a simulation, but what we can do is we can take the solution around the crystal and we can transform this solution into one that contains additives and this solution into one that does not. Okay, so the way that works is by an alchemical transformation. This is something that people who do protein design and enzyme design do all the time. They take a residue in the protein and they ask how would the stability or the folding rate change if I alchemically transformed this residue into another residue. So you're effectively doing reversible chemistry that would never be allowed, but in thermodynamics, the path that we take between 2 states doesn't really matter. And it's only the end states are what matters. Okay, so what we have then is a way of taking water molecules in our example and gradually converting them into sodium and chloride ions. So here we're taking the sodium and the chloride ions and we're transforming them into waters to get a pure water solution. And here we're taking some of the water molecules and we're transforming them into sodium and chloride ions. Now, if we do this in many stages, we can, for each stage, account the contribution to the reversible work for the overall process. And that is a theory that goes back to Zwanzig back in the 1950s, thermodynamic perturbation theory. So the results of this calculation, and here's the reference by Nathan Duff, published in J-Chem Phys in 2014. The results of this calculation are that when you start in water and you add brine, what happens is that the interfacial free energy drops by 7.7 millijoules per meter squared. That's a pretty sizable drop in the interfacial free energy, and I should note that that drop is averaged over all phases of this nucleus, not just for the charged phases. When you do the same calculation and you add 80 milligrams per liter of salt to a solution around an alpha glycine crystallite, then what happens is that the interfacial free energy of the gamma glycine increases by 3.1 millijoules per meter squared. Okay, so this is a bit of an unexpected result, right? We sort of knew that the effect of the salt would be to reduce the interfacial free energy in the gamma glycine case because it's a polar crystal. But we didn't know that the salt would have any appreciable effect on alpha glycine, and there was really no reason to even suspect that the sign of this would be positive. So these two results are consistent with experimental observations. If you look at work, for example, by Reg Tan in Singapore, he finds that if you crystallize gamma glycine in brine, if you crystallize glycine in a brine solution, you get gamma glycine, and if you crystallize glycine in an in a pure aqueous solution, you get the alpha polymorph. Okay, so at a qualitative level, these two results are consistent. We see that the brine enhances the rate of nucleation of the gamma glycine, and that the brine, according to our calculations, retards the rate of nucleation of alpha glycine. Now, it's not necessarily true for both of these two things to be true. I could just, enhance my gamma nucleation rate so much that I don't see alpha anymore. But actually, both of these two numbers are consistent with experiment, and we know that because you can look at work done by the Tan group, for example, in Singapore, and you can see that they have reported that the rate of nucleation of the alpha polymorph in water is actually faster than the rate of nucleation of the gamma polymorph in brine. And because we don't form the alpha polymorph in brine, we can infer that the rate of nucleation of the alpha polymorph in brine is actually slower yet than the nucleation of the gamma polymorph in brine. Now, taking these inequalities and stringing them all together, we see that the rate of nucleation of the alpha polymorph must get slower because we added brine, because we added salt to the solution, right? So that is in agreement with the sign of this result that we wouldn't have anticipated from the Debye-Huckel theory alone. And that gives us some confidence that what we're actually doing here is somewhat testable and predictive of real polymorph selection properties. So if you want to hear about this story, see the other video on polymorph selection.